In this video, we're going to take a look at what gravity looks like at interplanetary distances, like satellites, planets, stars, and galaxies. So far, we've been taking a look at what gravity looks like near the Earth, but when you go further away from the Earth, the force of gravity changes, it decreases. So let's take a look at what we've done so far and take a look at our new model of gravity. So far, let's see, if I have an object here above the Earth's surface, right here, I would say there's a force of gravity that acts, and the force of gravity is mg, that points down, mg. This is the ground level here. And just for sake of argument, I'm going to say that this is 1 meter above the ground. Okay, it's not going to be used in this calculation, but we will see how it comes into play a little bit later. So it's 1 meter above the ground. And for this example, I'm going to say this is a 100 kilogram object. 100 kilograms. Okay, so we would say the force of gravity, F, is equal to mg, and it's equal to 100 times 9.8 meters per second squared, which is 980 newtons. Okay. Now notice in this calculation, we did not take into account how far the object was from the Earth. We just said it's 100 kilograms times 9.8 meters per second squared. In other words, G is constant, doesn't matter where you're at, and we get 980 newtons. Well, when you go further away from the Earth, when you go very, very far, that's not so much the case. I'm going to do two calculations here. One when we're close to the Earth to compare to 980, and then we're going to go really, really far from the Earth and see what happens there. So I'm going to draw the Earth here. And I'm going to say there's our object that's 1 meter above the ground. This is not the scale, but it's 1 meter above the ground. And this here, we'll call it the radius of the Earth. Okay? And the force of gravity under this new law, or this new calculation, is equal to G, and I'll explain each one of these terms, m1, m2 over r squared. Okay, so what these are the following. G is a gravitational constant. It's just a number, which we'll see in a second. M1 and M2 are the two masses that we're talking about. So in this case, it's the mass, or 100 kilogram mass here, and it's the mass of the Earth. Okay, and r is the distance between the centers of the object. So the distance between the centers of the object is all the way down here, from center to center. Okay, so let's take a look at this, how this works out. G is, you'll see this in your equation sheet, is 6.67 times 10 to the minus 11th. It's the Newton's universal gravitational constant. It's used throughout the universe. It's just a fixed constant. Mass 1 is the mass of the first object. I'll just say it's the 100 kilogram object. And m2 is the mass of the second object, so in this case the Earth, which is 5.97 times 10 to the 24th kilograms. This is in kilograms as well. So these are both in kilograms. And then this is the distance between them squared. So it's the radius of the Earth, which you can look up, but it's 6.37 times 10 to the 6th meters. And then notice how I had this example 1 meter above the ground all the way to its center. I'm going to add that 1 meter, which in this case is going to be pretty inconsequential because it's 1 compared to 6.37 times 10 to the 6th, but I'll add it in there for completeness. And if you do this calculation, you'll get 981.34 newtons, which is actually pretty close to our other one. In fact, this is the exact one. This is an approximation. This is actually a little bit closer than you think. In our class, we've been using 9.8. The accepted value is 9.81 near the Earth, 9.81. So this becomes 981. So it's actually pretty close. It's off by 0.34 newtons. Okay, so for distances close to the Earth, our method, our old method, mg, is pretty good. It's pretty close. But let's see what happens when you get very, very far away from the Earth. So let's try this one more time. I'm going to take this mass and I'm going to move it an entire Earth radii above. So there's one Earth radii. I'll move it really far out there. So another Earth radii, RE. So it's a pretty large distance. How much force is acting on it when it's way out here? Let's see, in that case, F is equal to 6.67 times 10 to the minus 11th times that, still 100 kilograms because mass is constant throughout the universe, that doesn't change. And the mass of the Earth is still 5.97 times 10 to the 24th. And now the distance is a little bit different here. It's 6.37 times 10 to the 6. And then I'm going to move it another Earth radii, 6.37 times 10 to the 6, quantity squared. And if you do this, you get 245.33 newtons. So you can see there's a very huge difference there between the forces. So when we're close to the Earth, they're pretty similar, 981, 981. But if you go further away from there, very, very far, then you can see there's a big change. In fact, if we take a look at the relationship between these two, if I take a look at this force versus r, which is basically the height, we use r as our variable. If I took a look at this model here, the force of gravity, the magnitude of it, let's say, is mg. No matter what the height is, or what r is, how far I am, mg is the same. We don't take height into account. However, if we take a look at Newton's universal law of gravitation as a function of r, in other words, this equation right here, it's 1 over r squared. So what we do is we get a 1 over r squared type shape, an inverse square. So it asymptotically goes to 0. So these are definitely different. So when you're close to the Earth, we use this approximation, which is really when the distance is very, very small over here. But as you go to very large distances, then r drops off. This has other ramifications too. So as you recall, the amount of gravitational potential energy for an object is force times distance, or really the area under this curve, the integral of f dot dr. So that's the gravitational potential energy. However, if I look at the gravitational potential energy, if I go out to interstellar space, it's not simply a rectangle. It's a curve here, and I'd have to integrate a 1 over r squared curve to get the amount of gravitational potential energy. So there's a comparison between our old model of force, which is pretty accurate when you're close to the Earth, and the new model, Newton's universal law of gravity, that we have to use when we start to get to interstellar distances, when we get to very large distances. So g is our constant 6.67 times 10 minus 11th, mass of the two objects, and r is the center to center distance. I should have drawn center to center right here, although it's a very small distance here. However, if it were a planet, let's say a large planet like another planet here, we'd have to take into account this radius plus this distance between them plus this radii. So again, it's center to center distance. That's the key. And you can calculate the forces between the objects.